Hello there and welcome back to the Science Sleepy Minds. You're lying somewhere soft right now, perhaps beneath a familiar ceiling, perhaps wrapped in blankets that have memorized the shape of your body over countless nights just like this one. Outside your window, if you were to look, the sky stretches endlessly upward, sprinkled with ancient light from stars that may no longer even exist. You've seen this sky before. You've traced constellations with lazy fingers, wondered idly about what fills all that darkness between the pinpricks of brilliance. Tonight, we're going to talk about something hiding in that darkness, something so impossibly massive, so fundamentally wrong according to every physics textbook you might have skimmed in high school, that astronomers genuinely did not believe it could exist until very recently. This is not a black hole. You've heard plenty about black holes, those cosmic vacuum cleaners that swallow light and crush matter into oblivion. No, this is something stranger. Something that breaks the rules in ways black holes never dreamed of. Something that, if you were unlucky enough to encounter one up close, would probably vaporize you before your brain even registered that anything was wrong. But don't worry. They're all very, very far away, and most of them burned out billions of years before Earth was even a twinkle in the universe's eye. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. I would love to know where you're listening from tonight. Drop your location and local time in the comments, whether you're in Tokyo at 3 in the morning, or London at a sensible 11, or somewhere in the American Midwest where the crickets are singing their nightly chorus. We're all scattered across this little blue marble, but for the next little while, we're going to drift through the cosmos together. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Picture yourself standing in an open field on a moonless night. The grass beneath your bare feet is cool and slightly damp with evening dew. Above you, the Milky Way spills across the heavens like someone knocked over a jar of luminous powder. You have done this before, probably, this stargazing thing. You have tilted your head back until your neck complained and tried to wrap your mind around the sheer scale of what you were seeing. Each of those tiny points of light is a sun, some smaller than ours, some larger, many orbited by planets that might harbour their own strange forms of life. It is beautiful and humbling and, let's be honest, a little bit terrifying if you think about it too hard. But here is the thing about that familiar night sky. It has been lying to you. Not maliciously, of course. The sky does not have intentions, but the picture it paints is incomplete, like a postcard from a vacation that leaves out all the interesting disasters. What you see when you look up are the survivors, the well-behaved stars that follow the cosmic rulebook. They form from collapsing gas clouds. They burn hydrogen into helium in their cores. They live for millions or billions of years, and then they die in various spectacular fashions depending on their mass. Neat, tidy, predictable, at least in the grand scheme of things. What the sky does not show you are the monsters, the things that should not exist according to our best understanding of stellar physics. The cosmic anomalies that made astronomers spit out their coffee when the data first came through. Tonight, we are going to talk about one such monster in particular, an object so massive, so absurdly powerful, that it essentially told the laws of physics to take a seat and wait their turn. The funny thing about scientific understanding is that it always feels complete until it doesn't. In the late 19th century, physicists were fairly confident they had the universe more or less figured out. Classical mechanics worked beautifully. Thermodynamics made sense. Electromagnetism was elegantly unified by Maxwell's equations. Lord Kelvin reportedly declared that physics was essentially complete, with only a few minor clouds on the horizon. Those clouds, of course, turned out to be quantum mechanics and relativity. Two revolutionary frameworks that completely upended everything we thought we knew. Scientists still argue about whether Kelvin actually said this, or whether the quote has been embellished over the decades, but the lesson remains the same. Certainty is a dangerous drug. We find ourselves in a similar position today when it comes to stellar astrophysics. For most of the 20th century, the life cycles of stars seemed well understood. We knew how they were born in vast nebulae, how they spent their lives fusing lighter elements into heavier ones, and how they died, some fading quietly into white dwarfs, others exploding violently as supernovae, the most massive collapsing into neutron stars or black holes. The equations balanced, the observations matched the predictions, everything was comfortable, and then we started finding things that didn't fit, objects that were too massive to exist according to our models, phenomena that required explanations we hadn't invented yet. The universe, it turns out, has a sense of humour, and it delights in proving us wrong. You shift slightly in your bed, adjusting your pillow, and let out a long, slow breath. Above you, metaphorically speaking, the stars continue their ancient dance, indifferent to human comprehension. Somewhere out there, in the depths of space and time, monsters lurk. Some are familiar villains, black holes with their event horizons and singularities, neutron stars spinning faster than blender blades. But others are stranger. Others are theoretical whispers, ghosts in the data, objects that may have existed only in the universe's violent infancy. The one we are focusing on tonight goes by several names, but the most evocative is probably Quasi-Star. It sounds almost modest, doesn't it? Quasi meaning sort of, almost, not quite. But do not let the humble nomenclature fool you. A quasi-star, if such things ever existed, would be one of the most extreme objects the cosmos has ever produced. Imagine a star so enormous that it makes our sun look like a speck of dust. Now imagine that inside this gargantuan star, hidden within its blazing core, lurks a black hole. Not orbiting, not nearby, actually inside, like a parasite wearing its host as a disguise, feeding on the star's material while the outer layers continue to shine with impossible brilliance. This is the monster we are hunting tonight. This is the cosmic rule breaker that has given theoretical astrophysicists headaches and observational astronomers impossible homework assignments. It exists at the intersection of what we know and what we merely suspect, in that shadowy territory where mathematics meets imagination. But before we can understand what makes a quasi-star so special, we need to establish what normal stars are supposed to do. We need to learn the rules before we can appreciate just how dramatically they are being broken. So let's drift backward for a moment, away from the exotic and toward the familiar, and remind ourselves how ordinary stars live their ordinary lives. Think of it as laying the foundation before we blow up the building. You find yourself floating now, untethered from that grassy field, drifting through the void like a dandelion seed caught in a cosmic breeze. The destination is a stellar nursery, a vast cloud of gas and dust spanning light years, glowing faintly with the heat of infant stars struggling to be born. This is where it all begins, for every star that has ever shone and every star that ever will. The clouds themselves are beautiful in a ghostly sort of way, all swirling tendrils and luminous edges, painted in hues of red and gold and deep, bruised purple by the radiation of nearby stellar neighbours. The process of star formation is, at its heart, remarkably simple. You take a cloud of mostly hydrogen gas, sprinkle in some helium, and trace amounts of heavier elements, and then you wait. Gravity does the rest. Over millions of years, regions of slightly higher density begin to pull surrounding material inward. The cloud fragments, collapsing into clumps that grow denser and hotter as gravitational potential energy converts into thermal energy. It is like watching water circle a drain, except the drain is everywhere and the water is primordial hydrogen, and the whole thing takes longer than human civilization has existed. At the centre of each collapsing clump, pressure and temperature climb steadily higher. The gas becomes so hot that atoms are stripped of their electrons, creating a plasma that glows with increasing intensity. Eventually, the core reaches a critical threshold, roughly 10 million degrees Celsius, give or take, and something magical happens. Hydrogen nuclei, which have been bouncing off each other like stubborn billiard balls, finally overcome their mutual electromagnetic repulsion and fuse together. 4 hydrogen nuclei become one helium nucleus, and in the process, a tiny bit of mass is converted directly into energy, according to Einstein's famous equation. A star is born. This nuclear fusion is the heartbeat of every star in the universe. It is what makes the sun shine, what allows distant suns to warm alien worlds, what powered the first stars that ignited in the cosmic darkness billions of years ago. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, and as long as this equilibrium holds, the star remains stable. It is a delicate dance, really. Gravity trying to crush the star into oblivion, fusion trying to blow it apart. The two forces locked in a standoff that can last millions or billions of years depending on the star's mass. Here is where things get interesting, and by interesting, I mean slightly complicated, but I promise to keep it gentle. The mass of a star determines almost everything about its life and death. Small stars like red dwarfs burn their hydrogen fuel so slowly and efficiently that they can shine for trillions of years, far longer than the current age of the universe. They are the cosmic tortoises, plodding along while flashier stars burn bright and die young. Our own sun is somewhere in the middle, a comfortable yellow dwarf with a lifespan of about 10 billion years. We are currently a little over halfway through that, so no need to panic just yet. But the real drama happens at the upper end of the mass scale. Massive stars, those with 10, 20, 50 times the mass of the Sun, live fast and die hard. Their cores are so hot and so pressurized that fusion proceeds at a furious pace, burning through hydrogen reserves in mere millions of years rather than billions. These are the cosmic rock stars, blazing with incredible luminosity. Their surfaces so hot they glow blue-white. Their lives so brief that they barely have time to influence the planets that might orbit them. When a massive star exhausts its hydrogen, it doesn't simply fade away. Instead, the core contracts and heats up further, igniting helium fusion and producing carbon and oxygen. When helium runs out, the process repeats. Carbon fuses into heavier elements, then oxygen, then silicon, building up layers like a cosmic onion. Finally, the core produces iron, and here the star hits a wall. Iron fusion doesn't release energy, it absorbs it. Within seconds, the core collapses catastrophically, and the star explodes in a supernova so bright it can briefly outshine an entire galaxy. Astronomers have studied these life cycles extensively, and for the most part they match our theoretical predictions beautifully. We can look at a star's colour and brightness, and estimate its mass, its age, its likely fate. The Hertzsprung-Russell diagram, developed in the early 20th century, plots stars according to their luminosity and temperature, revealing clear patterns that correspond to different stages of stellar evolution. It is one of the great triumphs of astrophysics, a testament to human ingenuity and our ability to make sense of the cosmos from our tiny vantage point. But here is the catch, and there is always a catch when the universe is involved. Our models assume certain limits. One of the most important is something called the Eddington Limit, named after the British astrophysicist Arthur Eddington, who did pioneering work on stellar structure in the early 20th century. The Eddington Limit describes the maximum luminosity a star can achieve while remaining stable. Beyond this limit, the outward radiation pressure exceeds the inward gravitational pull, and the star begins to blow itself apart. According to this principle, stars cannot be arbitrarily massive. There is a ceiling, somewhere around 100 to 150 solar masses, beyond which a star simply cannot hold itself together. For decades, this seemed like a reasonable constraint. Observation supported it. The most massive stars we found were indeed in that range, and while they were impressive, they were not rule breakers. The universe appeared to be playing by the book, and then we started looking harder. We built better telescopes, we developed more sensitive instruments, we peered deeper into the cosmos and further back in time, and what we found was troubling. Not in a scary way necessarily, but in the way that any cherished assumption becomes troubling when evidence begins to contradict it. We found objects that were too massive, We detected signatures that didn't fit the models. We discovered, in short, that the universe had been hiding monsters from us. The first hints came from supermassive black holes. These colossal objects, millions or billions of times the mass of our Sun, lurk at the centres of most galaxies, including our own Milky Way. Their existence isn't particularly surprising. We've known about them for decades. What's surprising is how early they appeared. When astronomers looked at quasars, incredibly luminous galactic cores powered by accreting supermassive black holes, in the distant universe, they found some that existed less than 1 billion years after the Big Bang. This posed a serious problem. How could black holes have grown so massive so quickly? The standard model of black hole formation, a massive star explodes, leaves behind a stellar mass black hole. That black hole gradually accretes material and merges with other black holes over billions of years, simply couldn't account for such rapid growth. Something was missing. Some mechanism that could produce truly enormous black holes in the universe's infancy. And that something, some researchers began to suspect, might be a type of object that had never been directly observed. An object that existed only in theory, in equations scrawled on whiteboards and simulations running on supercomputers. An object that broke the rules we thought we understood. You shift again in your bed, feeling the weight of your eyelids beginning to assert itself. Outside, the night continues its slow rotation, carrying distant stars across the sky in their eternal parade. Somewhere in the darkness between those stars, the ghosts of ancient monsters may still be detectable, their light stretched and reddened by billions of years of cosmic expansion. We just have to know where to look. The year is 2019, and you can imagine the scene if you like. An office cluttered with papers and coffee cups, computer screens glowing with spectral data, a team of astronomers staring at their results with expressions that hover somewhere between excitement and disbelief. They have found something that shouldn't exist, something that defies the models they've spent their careers refining, something that is either a monumental discovery or a monumental error, and they genuinely aren't sure which. The object in question is called LB1, a designation that sounds more like a highway exit than a cosmic anomaly. But naming conventions in astronomy have never been particularly poetic. LB1 is located about 15,000 light-years from Earth, which is practically in our backyard by galactic standards. It's a binary system, meaning it consists of 2 objects orbiting each other. In this case, a normal-looking star and something invisible that was tugging on it gravitationally. Based on the wobble of the visible star, the team calculated the mass of its invisible companion. The number they got was 70 solar masses. To understand why this caused such a commotion, you need to remember what we discussed about stellar evolution and the limits on black hole formation. When massive stars die and collapse into black holes, there's an upper limit on how heavy those black holes can be. Stars between roughly 25 and 50 solar masses should, according to theory, produce black holes of maybe 10 to 20 solar masses. Some of the star's material is blown away in the supernova explosion, and some falls into the black hole. Stars more massive than about 50 solar masses were thought to undergo something called pair instability supernova, which completely destroy the star and leave nothing behind at all. This creates a mass gap in the black hole population. You should find black holes up to maybe 25 solar masses, then nothing until you get to the supermassive black holes at galactic centres. LB1's invisible companion, at 70 solar masses, sat squarely in this forbidden zone. It was too heavy to have formed from a normal stellar collapse, but too light to be a supermassive black hole. It was, in the parlance of astrophysics, impossible. The announcement made headlines around the world. Scientific journals published breathless articles. Social media erupted with discussions and debates. Some researchers immediately began looking for errors in the analysis, not out of spite, but because that's how science works. Extraordinary claims require extraordinary evidence, and a 70 solar mass black hole was about as extraordinary as claims get. And indeed, within months, other teams began poking holes in the original analysis. The wobble measurements were more ambiguous than initially reported. Alternative interpretations of the data suggested the companion might be significantly less massive, perhaps a more pedestrian 20 solar masses, well within the expected range. The controversy continues to this day, with different groups publishing different analyses, each claiming their methods are more accurate. Historians of science, and yes, there are such people, doing important work that often gets overlooked, still argue about whether LB1 was a genuine breakthrough or a cautionary tale about premature announcements. But here's the thing, even if LB1 itself turns out to be less exotic than initially claimed, the questions it raised remain unanswered. Where do supermassive black holes come from? How did they grow so large so quickly in the early universe? And could there be objects out there even stranger than the black holes we know? Objects that bend or break the rules in ways we haven't yet imagined. This is where the theoretical physicists enter the scene, stage left, carrying whiteboards covered in equations and expressions of barely contained excitement. Theoretical physicists are a particular breed. They spend their days imagining things that might exist, building mathematical models of hypothetical objects, and then handing those models to observational astronomers with a cheerful, "Go find this, would you?" Sometimes the observers find exactly what was predicted, and everyone celebrates. Sometimes they find something completely different, and the theorists go back to their whiteboards. Occasionally they find nothing at all, and a promising theory quietly fades into obscurity. The theory we're interested in tonight emerged from efforts to solve the supermassive black hole problem. If these colossal objects couldn't have grown from stellar mass black holes through normal accretion, then maybe they formed differently. Maybe, in the unique conditions of the early universe, there were pathways to creating massive black holes directly, without going through the intermediate step of stellar collapse at all. One such pathway involves something called a quasi-star. The term was coined in the 2000s, though the underlying concepts had been floating around theoretical circles for years before that. A quasi-star, in its simplest description, is a star with a black hole for a heart. Not a black hole orbiting a star, or a star falling into a black hole, but a single coherent object where the outer layers are stellar material, hot plasma undergoing fusion, and the inner region is a genuine black hole hidden from view, feeding on the star from within. If that sounds impossible, well, it should. Under normal circumstances, it would be. A black hole inside a star would quickly devour all the surrounding material, the outer layers would collapse, and you'd be left with just a black hole. End of story. But the early universe wasn't normal circumstances. In those first few 100 million years after the Big Bang, conditions were radically different from anything we experience today. The cosmic environment was hotter, denser, and almost entirely devoid of the heavy elements that now pervade interstellar space. These unique conditions might have allowed quasi-stars to form and survive for at least a little while, long enough to grow truly enormous black holes at their cores. The idea is still highly speculative. No one has ever observed a quasi-star directly, and given that they would have existed only in the universe's infancy, billions of years before Earth formed, no one ever will in any direct sense. But the mathematical models are intriguing, and they offer a potential solution to the puzzle of supermassive black hole origins. If quasi-stars existed, they might have been the seeds, the cosmic nurseries, that birthed the monsters now lurking at the hearts of galaxies. You let out a slow breath, feeling the tension in your shoulders begin to ease. The science is complicated, yes, but there's something almost soothing about it. The way human minds reach out across billions of light years and billions of years, trying to make sense of phenomena we will never experience firsthand. We tell ourselves stories about the cosmos, building narratives from fragments of light and mathematical inference, and those stories become our way of relating to the infinite. The funny thing about scientific discovery is that it often raises more questions than it answers. Every time we solve one mystery, we uncover 3 more hiding behind it. LB1 may or may not be what it first appeared to be. but the questions it prompted have led us somewhere fascinating, to theoretical monsters that may have stalked the universe in its youth, to black holes hidden inside stars, to the very edge of what our physics can describe. Let's venture a little closer to that edge, shall we? Let's talk about what a quasi-star might actually be, how it might form, and why it represents one of the most extreme objects that physics can even hypothetically allow. Picture a candle flame. You've seen thousands of them probably. Birthday candles, dinner candles, the little flickering glow of emergency candles during power outages. A candle flame is a simple thing, really. Wax melts, wicks burn, heat rises, and the whole system sustains itself in a delicate equilibrium. Now imagine that candle is the size of a star. Not our star, something much, much larger. And imagine that at the very centre of that flame, where the wick should be, there's a black hole. This is the quasi-star hypothesis in its most poetic form. It's a star that shouldn't exist. A luminous giant powered not just by nuclear fusion, as normal stars are, but also by the gravitational energy released as material falls into the black hole at its core. The two energy sources work together, maintaining the star's enormous envelope of plasma against the crushing pull of gravity. It's like a fusion reactor wrapped around a cosmic drain, with both systems feeding off each other in a temporary but spectacular symbiosis. The term quasi-star was introduced to distinguish these hypothetical objects from more familiar stellar phenomena. The prefix quasi means resembling or almost. A quasi-star resembles a star in some ways, but its internal structure and energy source are fundamentally different. It's a category that exists on the boundary between stars and black holes, partaking in the nature of both while being fully neither. To understand how a quasi-star might form, we need to rewind to the very beginning, not the beginning of the universe itself, but the beginning of the first stars. In the current epoch, star formation is seeded by heavy elements. When a cloud of gas collapses, atoms of carbon and oxygen and other elements radiate away excess heat, allowing the cloud to cool and condense efficiently. But in the early universe, before any stars had lived and died, there were no heavy elements. The cosmos contained only hydrogen, helium, and trace amounts of lithium, the products of primordial nucleosynthesis in the minutes following the Big Bang. Without heavy elements to cool the gas, the first stellar nurseries behaved differently. The collapsing clouds remained hotter, and the resulting stars, called population 3 stars in astronomical nomenclature, were much more massive than typical stars today. Some models suggest these primordial giants could have reached several hundred solar masses, perhaps even 1,000 or more. They would have been blazingly luminous, burning through their fuel in just a few million years before dying in catastrophic explosions that seeded the cosmos with the first heavy elements. But here's where it gets weird. In some scenarios, a collapsing primordial gas cloud could become so massive that it skips the normal star formation process entirely. Instead of settling into a stable equilibrium between gravity and fusion pressure, the core collapses directly into a black hole while the outer layers are still falling inward. The black hole forms at the centre of a still infalling envelope of gas, like the pit of a cherry materialising before the fruit itself is fully formed. Under ordinary circumstances, this would simply result in a black hole rapidly accreting all the surrounding material and then sitting there, invisible and alone, as black holes do. But in the unique conditions of the early universe, something different might happen. The gas falling toward the black hole is so dense and so hot that it generates tremendous outward pressure, radiation pressure from the photons produced as material heats up during infall. This outward pressure can actually slow and regulate the accretion, preventing the black hole from gobbling up everything at once. The result, if the models are correct, is a stable configuration, a black hole at the centre, surrounded by a massive envelope of hot gas that is continually falling inward but not falling in all at once. The gravitational energy released by this gradual accretion, combined with whatever nuclear fusion is occurring in the outer layers, keeps the whole structure inflated against gravity, It's a quasi-star, a temporary compromise between stellar and black hole physics, existing in a state that would be impossible under any other conditions. The scales involved are genuinely difficult to comprehend. A typical quasi-star model might have a total mass of several 100,000 to several million solar masses. The central black hole might start at a few thousand solar masses and grow as material continues to accrete. The outer envelope would extend for billions of kilometers, larger than the orbit of Neptune, larger than our entire solar system, a single bloated object of almost inconceivable size. One quirky detail that emerges from the models is that a quasi-star's surface would actually be relatively cool, despite the tremendous energy being generated inside. The enormous size means that the luminosity is spread over a vast surface area, so the temperature at any given point wouldn't be extreme. A quasi-star might glow with a dull reddish hue, like an ember the size of a solar system, rather than the brilliant blue-white of a compact hot star. There's something almost cozy about that image, isn't there? A cosmic ember, smouldering in the primordial darkness, harbouring a monster at its core. Scholars still debate the details. Some models suggest quasi-stars could only exist for a few million years, long enough to grow substantial black holes, but brief by cosmic standards. Others propose they might have persisted for tens of millions of years under the right conditions. The uncertainty stems from our limited understanding of the extreme physics involved. We've never seen a quasi-star, never measured one, never had any direct evidence that they exist or ever existed. Everything we know about them comes from computer simulations and mathematical models, which are only as good as the assumptions that go into them. What we can say with reasonable confidence is that if quasi-stars did exist, they would have been among the most extreme objects the universe has ever produced. They would have violated the Eddington limit that normally constrains stellar luminosity, sustained by accretion physics that allowed them to radiate energy at rates far exceeding what ordinary stars can achieve. They would have grown black holes at rates that normal accretion processes can't match. And when they finally died, when the black hole at their cores finally consumed the last of the surrounding gas, they would have left behind seeds for the supermassive black holes we now observe at the centres of galaxies. It's a beautiful theory in its way. It solves a real problem in our understanding of the universe. But like all beautiful theories, it awaits the verdict of observation. Somewhere out there, perhaps, ancient light from quasi-stars is still travelling toward us, stretched and reddened by billions of years of cosmic expansion. If we're clever enough and patient enough, we might someday catch it. You're drifting now, further back than you've ever been, to a time when the universe itself was young and strange and nothing like the orderly cosmos you learned about in school. 13 billion years ago, give or take, the darkness was just beginning to lift. The cosmic microwave background, that ancient afterglow of the Big Bang, had already cooled and faded from brilliant white to dull infrared to invisible microwave whispers. The first atoms had formed, mostly hydrogen with a smattering of helium, and they floated in vast clouds through an expanding void that contained no stars, no galaxies, no planets, no life, just gas and darkness, waiting for something to happen. This epoch is sometimes called the Cosmic Dark Ages, which is both accurate and evocative. For roughly 100 million years after the Big Bang, there were no sources of visible light anywhere in the universe. The cosmos was opaque to our intuitions, a vast, cold, silent expanse where nothing particularly interesting seemed to be happening. But beneath that apparent stillness, gravity was working. The tiny density fluctuations imprinted during cosmic inflation, quantum ripples magnified to astronomical scales, were slowly pulling matter together. Regions slightly denser than average attracted more gas, grew denser still, and eventually collapsed into the first luminous objects. When those first stars ignited, they transformed the universe. Suddenly, there was light. Not the relic radiation of the Big Bang, but fresh photons produced by nuclear fusion, blazing out into the darkness from sources that hadn't existed moments before. This moment is called cosmic dawn, and it marks one of the most significant transitions in the history of everything. Before it, darkness. After it, stars. The conditions during cosmic dawn were radically different from anything we experience in the present-day universe. The gas was pristine, completely untouched by stellar nucleosynthesis. No carbon, no oxygen, no iron, no silicon. None of the elements that now make up rocky planets and living organisms. Just hydrogen and helium in roughly the same proportions they had possessed since the first few minutes after the Big Bang. This primordial composition had profound implications for how the first stars formed and how massive they could become. In the modern universe, star formation is mediated by heavy elements. When a gas cloud collapses, atoms of carbon and oxygen and other elements emit photons at specific wavelengths, carrying away energy and allowing the cloud to cool. This cooling is essential. It allows the gas to condense into dense cores that eventually ignite fusion. Without it, the collapsing cloud would remain too hot and too diffuse to form stars efficiently. But in the primordial universe, there were no heavy elements to provide this cooling. The only cooling mechanism available was the much less efficient radiation from hydrogen molecules, pairs of hydrogen atoms bound together, capable of emitting photons but only weakly. As a result, primordial gas clouds couldn't cool as effectively, and they had to accumulate much more mass before collapsing. The first stars, born from these massive clouds, were correspondingly enormous, perhaps hundreds of times more massive than the Sun, perhaps even more. These population 3 stars, as astronomers call them, would have been unlike anything in the current universe. They burned hot and bright, with surface temperatures exceeding 100,000 degrees and luminosities millions of times greater than the Sun. They consumed their fuel at prodigious rates, living fast and dying young, perhaps only a few million years from ignition to explosion. When they died, they enriched the surrounding gas with the first heavy elements, setting the stage for subsequent generations of stars that could form more easily and more abundantly. But population 3 stars were just one possibility for what the primordial universe could produce. In some scenarios, the collapsing gas clouds were so massive that they couldn't form ordinary stars at all. Instead, they underwent what's called direct collapse, a runaway gravitational implosion that produced black holes directly, without an intervening stellar phase. These direct collapse black holes could have been much more massive than anything formed by normal stellar evolution, providing another potential pathway to the supermassive black holes we observe today. And then there's the quasi-star scenario, which occupies a kind of middle ground between these extremes. In this picture, the collapsing cloud is massive enough to form a black hole at its centre, but not so massive that everything falls in immediately. Instead, the outer layers remain suspended around the central black hole, sustained by the energy released from accretion. The result is a hybrid object, part star, part black hole, wholly unprecedented. The conditions required for quasi-star formation were probably quite specific. The gas cloud had to be in a particular mass range, too small, and it would form a normal massive star, too large, and it would collapse directly into a black hole without the intermediate quasi-star phase. The environment had to be relatively quiet, without nearby stars or galaxies disrupting the collapse, and the whole process had to occur during a narrow window of cosmic history, before the universe became polluted with heavy elements that would change the physics of star formation. These restrictive requirements explain why quasi-stars, if they existed, would have been rare. They weren't the dominant population of primordial objects, but rather exotic outliers that formed only under exceptional circumstances. And because they were rare, and because they existed only in the distant past, we have no hope of observing one directly. We can only infer their existence, if we can infer it at all, from the traces they might have left behind. One quirky prediction of quasi-star models is that they might have produced distinctive gravitational wave signatures. When the central black hole merged with other black holes or neutron stars, perhaps drawn into the quasi-star by its enormous gravity, the resulting ripples in space-time would have had characteristic frequencies and amplitudes. Future gravitational wave detectors, more sensitive than our current instruments, might be able to identify these ancient signals amid the cosmic background noise. It's a long shot, but it's one of the few ways we might ever get direct evidence for these theoretical monsters. For now, quasi-stars remain ghosts, beautiful, compelling, theoretically necessary ghosts, but ghosts nonetheless. They haunt our models and tantalize our imaginations, existing in that liminal space between what we know and what we merely suspect. In the darkness of the early universe, they may have blazed with impossible light, growing monsters at their cores. Or they may never have existed at all, victims of our incomplete understanding of primordial physics. The uncertainty, I think, is part of what makes them fascinating. Science is often presented as a collection of facts, but it's really a process of gradually reducing uncertainty, a slow, asymptotic approach toward truth, never quite arriving. Quasi-stars represent one of the frontiers of that approach, a place where theory reaches beyond observation and dares to imagine what might be. There's a rule in physics that sounds almost too simple to be profound. It says essentially that you can't have everything. You can't have unlimited energy output. You can't have infinite brightness. You can't build a star of arbitrary size and expect it to hold together. The universe imposes limits, and those limits are not suggestions. They are fundamental constraints woven into the fabric of physical law. The most famous of these limits, at least in the context of stellar physics, is the Eddington Limit. Named after Arthur Stanley Eddington, a British astrophysicist who worked in the early 20th century, this limit defines the maximum luminosity that a star can achieve while remaining in hydrostatic equilibrium. Beyond this threshold, the outward pressure of radiation exceeds the inward pull of gravity, and the star begins to lose mass in furious stellar winds or outright blow itself apart. Eddington was a fascinating figure, one of those polymaths who seemed to excel at everything he touched. He was among the first to correctly understand how energy is generated in stellar cores, proposing that nuclear fusion was the source of the sun's power decades before the relevant physics was fully worked out. He led the expedition that confirmed Einstein's general theory of relativity by measuring the bending of starlight during a solar eclipse. He wrote popular science books that made complex physics accessible to general audiences, and, perhaps most relevant to our story tonight, he developed the theoretical framework for understanding how radiation pressure and gravity interact inside stars. The Eddington Limit emerges from a simple competition. Inside a star, photons are constantly being produced by nuclear fusion. These photons carry momentum, and as they travel outward through the stellar material, they transfer that momentum to the atoms they encounter. This creates an outward pressure, radiation pressure, that pushes against the star's tendency to collapse under its own gravity. In a stable star, these two forces are balanced. Gravity pulls inward, radiation pushes outward, and the star maintains its size. But this balance has limits. As a star becomes more massive, its luminosity increases dramatically, roughly as the cube of its mass for stars on the main sequence. At the same time, the gravitational pull at the surface increases only linearly with mass. This means that for sufficiently massive stars, the radiation pressure eventually overcomes gravity. The star begins to shed its outer layers, driven off by the relentless outward push of photons. In extreme cases, the star can become unstable entirely, unable to maintain any coherent structure. The exact mass at which this occurs depends on various factors: the star's composition, its structure, the opacity of its outer layers to radiation. But for typical stellar compositions, the Eddington Limit kicks in somewhere around 100 to 150 solar masses. Stars more massive than this are expected to be rare, unstable, and short-lived. They should blow off mass until they reach a stable configuration below the limit, or else disrupt themselves entirely. This is the rule that quasi-stars break. If they exist, they would have been far more massive than the Eddington Limit allows, potentially millions of solar masses, dwarfing even the most extreme normal stars by factors of thousands. How is this possible? How can an object be so massive and yet not tear itself apart? The answer lies in the geometry of accretion. In a normal star, energy is generated in the core and must travel outward through the entire mass of the star to reach the surface. This journey is slow and inefficient. A photon produced in the sun's core takes roughly 100,000 years to random walk its way to the surface, bouncing off atom after atom along the way. The opacity of the stellar interior determines how effectively radiation pressure can be transferred to the stellar material, and for normal stellar compositions that opacity is high. But in a quasi-star, the energy source is different. Much of the luminosity comes not from nuclear fusion in the outer layers, but from gravitational energy released as material falls into the central black hole. This accretion energy is generated in a relatively small region near the black hole, and it radiates outward through a convective envelope rather than a radiative one. The convection, the churning, boiling motion of hot gas rising and cool gas sinking, transports energy far more efficiently than radiation alone. This changes the dynamics entirely. In a convective envelope, the effective opacity is much lower. The energy doesn't have to push its way through static material. Instead, it's carried by bulk fluid motion, bypassing the normal radiation pressure limits. This allows a quasi-star to support a much larger mass than the Eddington Limit would normally allow. The energy is transported differently, and so the rules are different. There's also another factor at play: the reservoir of gravitational energy available from accretion. When material falls into a black hole, it releases roughly 10% of its rest mass energy, a fantastically efficient process compared to nuclear fusion, which converts only about 0.7% of mass into energy. This means that even though a quasi-star might have only a few thousand solar masses worth of nuclear fuel, it has access to vastly more energy from the accretion process. The black hole at its core acts like a supercharger, boosting the total energy output far beyond what fusion alone could provide. The result is an object that defies our normal intuitions about stellar limits. A quasi-star can be enormous, luminous, and stable, at least for a while, because it operates under different physical principles than ordinary stars. It's a bit like discovering that the speed limit on a highway doesn't apply to vehicles that use a different propulsion system. The limit is still real, still physically grounded, but there are loopholes for sufficiently exotic configurations. Astronomers still argue about the details. Some models suggest that quasi-stars could only exist for a few million years before the central black hole consumed the surrounding envelope entirely. Others propose longer lifetimes under certain conditions. The uncertainty reflects the limits of our current understanding. We're extrapolating from known physics into regimes that have never been observed, and there's always room for surprises. But the basic concept is robust. Accretion physics allows for structures that fusion physics alone cannot support. And in the early universe, where conditions were ripe for extreme accretion, quasi-stars may have been the cosmic monsters that broke the rules and seeded the supermassive black holes we see today. Imagine a heart that beats with gravity rather than muscle. Imagine a core that doesn't pump blood but swallows light. Imagine a creature so massive that it takes millions of years for information to travel from its center to its surface, yet so violent that matter falls into its heart at nearly the speed of light. This is the quasi-star, an object with a black hole hidden inside it, feeding and growing while the outer layers continue to shine. The mechanics of how this works are genuinely strange, even by astrophysical standards. In a normal star, the core is the hottest and densest region, where nuclear fusion generates the energy that keeps the whole structure inflated against gravity. The core is solid in a metaphorical sense. There's nothing inside it, no void or absence, just increasingly compressed plasma until you reach the very center. But in a quasi-star, the core isn't there. Where the core should be, there's a black hole, a region of space-time so warped that nothing, not even light, can escape. This black hole forms during the initial collapse of the proto-quasi-star. As the primordial gas cloud contracts, the centre becomes increasingly hot and dense. At some point, the conditions become extreme enough that the core can no longer support itself against gravity through any known mechanism. Not radiation pressure, not degeneracy pressure, not any of the normal forces that keep stars stable. The core collapses directly into a black hole, leaving behind an event horizon, a boundary beyond which all paths lead inward. Now, under normal circumstances, this would be the end of the story. The black hole would continue to pull in surrounding material, growing as it devoured everything nearby, until nothing was left but the black hole itself and whatever accretion disk might temporarily swirl around it. This is what happens when massive stars die and form stellar mass black holes. The collapse is catastrophic and total, leaving behind only the gravitational corpse. But in a quasi-star, the collapse is incomplete. The outer layers of the collapsing cloud are still falling inward, but they haven't reached the centre yet. There's a traffic jam of gas, billions of kilometres of it, surrounding the newly formed black hole and pressing inward under tremendous gravitational force. This infalling material is dense and hot, and as it approaches the black hole, it releases enormous amounts of gravitational potential energy. This energy radiates outward, creating pressure that slows and regulates the infall. The result is a strange equilibrium. The black hole sits at the centre, hungrily consuming whatever material reaches its event horizon. But the rate of consumption is limited by the Eddington Limit on accretion. The same principle that limits stellar luminosity also limits how fast a black hole can eat. Above a certain accretion rate, the radiation pressure from infalling material actually pushes back against the infall, throttling the flow. The black hole eats, but it eats slowly, at least by astrophysical standards. Meanwhile, the outer layers of the quasi-star remain suspended around this feeding black hole, kept aloft by the energy radiating outward. There might be some nuclear fusion occurring in these outer layers, hydrogen fusing into helium perhaps, in the cooler regions far from the core. But the dominant energy source is gravitational. The quasi-star shines primarily because material is falling into a black hole at its centre, not because atoms are merging in its depths. This configuration is sometimes described as parasitic, which captures something true about it. The black hole is feeding on its host, consuming the star from within, growing larger as the outer layers shrink. Eventually, inevitably, the black hole will win. It will devour the surrounding envelope entirely, emerging as a bare black hole perhaps 100,000 solar masses heavy, the seed of a future supermassive black hole. The quasi-star is doomed from birth, its fate sealed by the monster growing in its heart. There's a certain poignancy to this, isn't there? The quasi-star shines brightly, visible perhaps across the entire universe, a beacon of light in the cosmic dark ages, and all the while, it's being consumed from within. Its beauty is the product of its destruction. Its luminosity is the signature of its dying. Every photon that escapes represents a tiny bit of mass that has fallen past the point of no return. One detail that emerges from the models is the structure of the interface between the black hole and the surrounding envelope. This isn't a sharp boundary. You don't have stellar material on one side and empty space-time on the other. Instead, there's a transition zone, a region where the gravitational effects of the black hole become dominant and the gas begins its final plunge inward. This region is incredibly hot and dense, a maelstrom of plasma spiralling toward oblivion. Astronomers call this region the innermost stable circular orbit, or ISCO for short. Inside the ISCO there are no stable orbits. Material inevitably falls into the black hole. Outside the ISCO, gas can orbit for extended periods, gradually losing energy and spiralling inward. The ISCO acts like a cosmic drain, defining the boundary between the part of the quasi-star that still has some structural integrity and the part that has already begun its final journey. The temperatures near the ISCO are extreme, millions of degrees, hot enough that thermal radiation peaks in the X-ray portion of the spectrum. If you could somehow observe a quasi-star from up close, You would see a dim, reddish giant on the outside, deceptively calm, with a blazing furnace hidden at its core. The contrast between the surface and the centre would be almost comical if it weren't so violent. Scholars still debate whether quasi-stars could maintain this configuration for millions of years, as some models suggest, or whether they would be much shorter-lived. The answer depends on factors like the accretion rate, the mass of the initial black hole, and the structure of the surrounding envelope, all of which are poorly constrained by current observations. What we can say is that the basic physics seems sound. A black hole can hide inside a star, feeding and growing, for at least some period of time. The universe allows this configuration, even if it doesn't guarantee it. And somewhere in the ancient cosmos, during those first few 100 million years when the rules were still being written, quasi-stars may have blazed briefly and died spectacularly, leaving behind the seeds of everything that came after. Let's pause for a moment and try to wrap our heads around the scale of these objects. Scale is difficult. Our brains evolved to understand things like fruit trees and predators, and distances we could walk in a day. They didn't evolve to comprehend stellar masses or light-year distances or time spans of billions of years. But we can try, and in trying, we might approach something like genuine awe. Start with the Sun. Our Sun is a fairly average star, a yellow dwarf about 4.6 billion years old, roughly halfway through its expected lifespan. It contains about 99.86% of all the mass in our solar system. Every planet, every moon, every asteroid, every comet, every speck of dust, all of it together amounts to barely a rounding error compared to the Sun. The Sun is about 1.4 million kilometers in diameter, which means you could line up about 109 Earths across its face. If the Sun were hollow, you could fit roughly 1.3 million Earths inside it. Big, in other words. Very big. Now imagine that the Sun is a marble, a little glass sphere, the kind you might have played with as a child. On this scale, the Earth would be a grain of sand about 12 meters away. Jupiter would be a small pea roughly 60 meters distant. Neptune, the outermost planet, would be a pinhead nearly half a kilometer from the marble. On this same scale, a quasi-star would be roughly the size of a football stadium. Not the field, the entire stadium, including the stands, the parking lots, the concourse, everything. If you placed our marble Sun at the centre of this stadium quasi-star, it would be utterly lost. A tiny spark drowning in a sea of luminous gas, billions of times more voluminous. The mass ratios are even more extreme. A large quasi-star might contain millions of solar masses. That's millions of marble suns, compressed into a single bloated structure. The black hole at the centre might itself be tens of thousands of solar masses, larger than any stellar mass black hole in the modern universe, but still just a tiny fraction of the total quasi-star mass. The outer envelope, the part that makes the quasi-star look like a star at all, might span billions of kilometers, engulfing a volume larger than our entire planetary system. Here's a fun comparison. If you replaced our Sun with a quasi-star, the quasi-star's surface would extend well beyond the orbit of Neptune. Pluto, out in the Kuiper Belt, would be inside this bloated monster. Everything we consider our solar system, all the planets, all the moons, all the comets and asteroids, would be contained within a single star. You wouldn't orbit it, you'd be part of it, engulfed by its diffuse outer layers, slowly spiralling inward toward the black hole at its core. The luminosity of a quasi-star would be correspondingly enormous. Our Sun produces about 3.8 times 10 to the power of 26 watts of power, a number so large it's essentially meaningless to human intuition. But a quasi-star might be millions of times more luminous still. If you were a hypothetical observer in the early universe, a quasi-star would appear as one of the brightest objects in the sky, visible from billions of light-years away. It would outshine entire galaxies, a single colossal beacon in the primordial darkness. And yet, paradoxically, the surface of this incredibly luminous object would be relatively cool. This seems counterintuitive until you remember that luminosity depends on both temperature and surface area. The Sun's surface is about 5,500 degrees Celsius, hot enough to glow yellow-white. But a quasi-star, despite being millions of times more luminous, might have a surface temperature of only 4,000 to 5,000 degrees, reddish, like a dying ember. The enormous surface area more than compensates for the lower temperature, spreading the light across such a vast expanse that the total output still dwarfs anything we know. Imagine looking at a quasi-star from some impossible vantage point, close enough to see it clearly, but far enough to survive. What would you see? A reddish sphere the size of a solar system, glowing with a dull but steady light. No sharply defined surface, really, just a gradual thinning of the luminous gas until it fades into the background darkness. No visible features like sunspots or flares. The outer layers would be too diffuse, too gently churning for such dramatic structures. Just an enormous, softly glowing presence, dominating your field of view like a god-made manifest. And at the centre, invisible but omnipresent, the black hole. You wouldn't see it. Black holes don't emit light by definition. But you might sense its influence, the way matter streams inward from all directions, the way the inner regions of the quasi-star swirl and compress. The black hole is the heart of this monster, the reason it exists, the engine of its destruction. Without the black hole, the quasi-star would just be an extremely massive cloud of gas, collapsing under its own gravity. With the black hole, it becomes something unprecedented, a star-shaped cocoon nurturing a cosmic predator. The lifetimes of quasi-stars are measured in millions of years, long by human standards, but brief by cosmic ones. During that time, the black hole grows steadily, consuming perhaps a solar mass of material per year. When the envelope is finally exhausted, the quasi-star dies, not in a dramatic explosion, but in a gradual dimming, the luminous outer layers finally surrendering to the hunger at the core. What remains is a black hole, perhaps 100,000 solar masses sitting alone in space, ready to grow further through mergers and accretion, ready to become, eventually, the supermassive monster at the heart of a galaxy. The scale is humbling, the implications are staggering, and the fact that all of this might have happened billions of years ago in a universe we can barely glimpse, well, that's the kind of thing that either keeps you awake at night or puts you right to sleep, depending on your disposition. Let's hope it's the latter tonight. You find yourself drifting through the darkness now, imagining what it would have been like to witness a quasi-star in its full glory. The light would have been something special, not harsh and blinding like the blue-white glare of massive modern stars, but warm and persistent, a steady glow that painted the surrounding space in hues of deep crimson and amber. This is the kind of light that doesn't assault the eyes, but instead invites you to stare, to wonder, to lose yourself in its diffuse radiance. The luminosity of a quasi-star, we've established, would be extraordinary, millions of times brighter than our sun, perhaps billions in some models. But what does that actually mean for an observer? What would you experience if you could somehow travel back 13 billion years and watch one of these monsters shine? First, distance matters enormously. The universe is vast beyond comprehension, and even the brightest objects fade with distance according to the inverse square law. A quasi-star a billion light-years away would appear as a mere pinprick of light, indistinguishable from a much smaller, closer star except through careful spectroscopic analysis. You might not even notice it amid the general stellar background, assuming there was a stellar background to speak of, which in the early universe there mostly wasn't. But if you were closer, say a few thousand light-years, the picture changes dramatically. At that distance, a quasi-star would be one of the brightest objects in your sky, easily visible to the naked eye even during daylight. If daylight existed, which it probably didn't for any planets orbiting nearby, it would be a soft reddish beacon, hanging in the darkness like a lantern left burning by some cosmic caretaker. Ancient and patient, it would shine steadily for millions of years, a reliable landmark in an otherwise chaotic young universe. The light from a quasi-star would have unique characteristics. Because the surface temperature is relatively low, around 4,000 to 5,000 Kelvin, the peak emission would be in the red and infrared portions of the spectrum. Visible to human eyes, certainly, but dominated by wavelengths we perceive as warm and cozy rather than harsh and energetic. This is perhaps one of the stranger aspects of quasi-stars. Despite being powered by one of the most violent processes in the universe, matter falling into a black hole, they would appear gentle from the outside, deceptive in a way. Of course, the inner regions would be anything but gentle. Near the central black hole, temperatures would soar into the millions of degrees, producing copious X-ray and gamma-ray emission. This high-energy radiation would be mostly absorbed by the surrounding envelope before it could escape, converted into the softer radiation that emerges from the surface. The quasi-star acts like a cosmic filter, taking the brutal output of accretion and laundering it into something less aggressive. For astronomers in the early universe, hypothetical astronomers of course, since no intelligent life existed at that point, quasi-stars would have been fascinating targets. Their spectra would show signatures of the pristine primordial gas, lots of hydrogen, some helium, essentially no heavy elements. This would mark them immediately as something ancient and unusual, relics of a time before stellar nucleosynthesis had begun to pollute the cosmos with carbon and oxygen and iron. Here's a quirky thought. A civilization orbiting a quasi-star would have a very different relationship with the sky than we do. For us, the sun dominates, a single bright point that rises and sets, marking our days and seasons. But a quasi-star is so enormous that it would span a significant portion of the sky from any reasonable distance. If you were on a planet orbiting a few billion kilometers out, the quasi-star wouldn't look like a point at all. It would look like a wall of dull red light, stretching from horizon to horizon, warming you with its diffuse glow. Day and night as we understand them wouldn't exist. There would just be the constant presence of the star, the eternal ember filling half your sky. Such a planet probably couldn't exist, of course. The gravitational dynamics near a quasi-star would be extreme, the radiation environment challenging even at great distances. But it's a fun thought experiment, a way of grounding these abstract numbers in something approaching human experience. The light from quasi-stars, if they existed, has long since washed over us and continued past. We're talking about objects that formed and died within the first billion years of cosmic history, and the universe is now nearly 14 billion years old. Any photons produced by quasi-stars have been travelling through expanding space for all that time, their wavelengths stretched by cosmic redshift until the original visible light has been pushed into the infrared or even microwave portions of the spectrum. This is one of the great challenges in searching for evidence of quasi-stars. The light is there, potentially, encoded in the cosmic background, but it's old and faint and redshifted beyond easy recognition. You can't just point a normal telescope at the sky and hope to spot one. You need specialized instruments capable of detecting faint infrared signals amid the noise, and you need sophisticated analysis to distinguish a quasi-star signature from other sources of ancient light. The James Webb Space Telescope, which we'll discuss more later, is designed precisely for this kind of work. Its infrared sensitivity allows it to peer back toward the cosmic dawn, searching for the first luminous objects to emerge from the darkness. Whether it can actually detect quasi-stars, if quasi-stars existed, remains to be seen. The signals might be too faint, too redshifted, too confused with other sources, but the attempt is being made, and that itself is a kind of triumph. Scholars still argue about what a quasi-star signature would actually look like in modern observations. Some models predict distinctive spectral features, absorption and emission lines, that would mark an object as powered by accretion rather than fusion. Others suggest that quasi-stars would be indistinguishable from very massive normal stars at the distances involved. The debate continues, fueled by theoretical predictions that have yet to be tested against observation. And somewhere out there, perhaps, the ancient light is waiting, a faint whisper from the cosmic dawn, carrying information about objects that no longer exist, encoded in patterns of electromagnetic radiation that have travelled billions of years to reach us. All we have to do is be clever enough to read it. There's a frustrating truth at the heart of this story, and we might as well confront it now. We have never seen a quasi-star, not directly, not indirectly, not even circumstantially with enough confidence to publish. Everything we've discussed so far, the massive envelopes, the hidden black holes, the luminosities rivaling galaxies, exists only in theory, in mathematical models running on supercomputers, in equations scrawled on whiteboards by astrophysicists with very particular interests. This isn't unusual in science. Many of the most important theoretical entities were predicted long before they were observed. The neutrino, proposed in 1930, wasn't detected until 1956. The Higgs boson, theorized in 1964, wasn't confirmed until 2012. Gravitational waves, predicted by Einstein in 1916, weren't directly detected until 2015. The pattern is familiar. Someone does the math suggests something should exist, and then we spend decades or centuries building instruments sensitive enough to find it. Quasi-stars are in that intermediate phase. The math suggests they could have existed under the right conditions. The physics allows them, even if barely. But the conditions were so specific. Primordial composition, massive gas clouds, the unique environment of the early universe, that they would have been rare even at their peak. And now, 13 billion years later, they're gone. Every quasi-star that ever existed has long since burned out, its envelope consumed, its black hole core left behind as a seed for something larger. So if we can't see them, how can we ever know if they were real? The answer lies in indirect evidence. We might not be able to observe quasi-stars themselves, but we might be able to observe their consequences. If quasi-stars existed, they would have left marks on the universe, signatures that we can potentially detect even billions of years later. The most important consequence is the supermassive black holes themselves. As we discussed earlier, one of the great puzzles in astrophysics is how these enormous objects grew so large so quickly. Standard accretion models struggle to explain supermassive black holes existing within the first billion years after the Big Bang. But if quasi-stars provided a shortcut, a way to create black holes of tens of thousands of solar masses in one fell swoop, then the puzzle becomes more manageable. The black hole seeds from quasi-stars could have grown through normal accretion and mergers over the subsequent billions of years, eventually reaching the millions or billions of solar masses we observe today. This argument is circumstantial, of course. The existence of supermassive black holes doesn't prove that quasi-stars existed. It just suggests that some efficient seed formation mechanism was at work. There could be other explanations: direct collapse black holes, primordial black holes from the Big Bang, or mechanisms we haven't thought of yet. But quasi-stars remain one of the most compelling possibilities, and their theoretical properties align well with what we need to solve the puzzle. Another potential line of evidence comes from gravitational waves. When black holes merge, they produce ripples in space-time that propagate outward at the speed of light. We've been detecting these gravitational waves since 2015, and each detection tells us something about the masses and spins of the merging black holes. If quasi-stars produce black holes in a particular mass range, say tens of thousands of solar masses, we might eventually detect mergers involving these intermediate mass black holes. Such detections would be strong evidence that something like quasi-stars existed in the early universe. The challenge is that intermediate mass black holes are hard to detect with current instruments. LIGO and Virgo, our most sensitive gravitational wave detectors, are optimized for stellar mass black holes, objects of a few to a few dozen solar masses. Supermassive black holes, on the other hand, produce gravitational waves at frequencies too low for ground-based detectors. Intermediate mass black holes fall in a gap, producing signals that are difficult to detect with either current technology. Future missions like LISA, a space-based gravitational wave observatory planned for the 2030s, might be better suited to finding them. There's also the possibility of detecting signatures in the cosmic microwave background, the afterglow of the Big Bang itself. The CMB is exquisitely sensitive to conditions in the early universe, and any significant energy injection from quasi-stars could have left imprints. The details are complex and model-dependent, but some researchers have proposed that future CMB measurements might reveal traces of the quasi-star era. And then there's the direct approach, looking for the light itself. This is where the James Webb Space Telescope enters the story. JWST is specifically designed to observe the early universe, using its infrared sensitivity to peer back toward the cosmic dawn. If quasi-stars were luminous enough, and they should have been enormously luminous, their light might still be detectable as faint infrared sources in the distant universe. The problem is distinguishing a quasi-star from other bright sources. At the distances involved, even the brightest quasi-star would appear as a point source, indistinguishable by shape from a normal star or a small galaxy. The identification would have to come from spectroscopy, analysing the light to determine the chemical composition and physical conditions of the emitting object. A quasi-star spectrum would show the signatures of pristine primordial gas, unlike the heavy element-enriched spectra of modern stars. Scholars debate whether JWST has the sensitivity to make such detections. Some models suggest that quasi-stars could have been bright enough to be within reach. Others are more pessimistic. The truth is that we won't know until we look, and looking is exactly what JWST is doing right now, as you lie in your bed and drift towards sleep. Somewhere in the data streaming back from that telescope, encoded in patterns of infrared photons, there might be evidence of quasi-stars, or there might not. The universe keeps its secrets well, and we're still learning how to ask the right questions. Let's talk about seeds, not the kind you plant in gardens, though there's a metaphorical connection, but the kind that grow into the most massive structures in the universe. Supermassive black holes, those gravitational giants lurking at the centres of galaxies, had to start somewhere. They didn't spring into existence fully formed, billions of solar masses heavy, ready to anchor entire galactic systems. They grew from smaller beginnings, accreting matter over cosmic time, merging with other black holes, gradually becoming the monsters we observe today. But what were those smaller beginnings? Where did the first seeds come from? This is one of the central questions in modern astrophysics, and the answer remains frustratingly elusive. We've observed supermassive black holes powering quasars less than 1 billion years after the Big Bang, which places severe constraints on how quickly they must have formed. Standard astrophysics offers a few possibilities, each with its own strengths and weaknesses. The most straightforward option is stellar mass black holes, the remnants of massive stars that have exploded as supernovae. These black holes typically weigh a few to a few dozen solar masses, and they form regularly throughout the universe wherever massive stars live and die. In principle, a stellar mass black hole could grow into a supermassive one through billions of years of accretion and mergers. In practice, the growth rate is limited by the Eddington Limit we discussed earlier. Even accreting at the maximum possible rate, a stellar mass black hole would struggle to reach supermassive status in less than 1 billion years. The math just doesn't work out. This is where heavier seeds become necessary. If the initial black hole was already much more massive, say 10,000 or 100,000 solar masses, then the growth timeline becomes more manageable. The black hole starts closer to its final mass and has less distance to cover. But where do these heavy seeds come from? One possibility is direct collapse. In certain rare conditions, a massive gas cloud might collapse directly into a black hole without ever forming a star at all. This requires the absence of heavy elements to prevent efficient cooling and fragmentation, and a strong background of ultraviolet radiation to keep the gas hot and prevent molecular hydrogen from forming. If these conditions are met, the cloud can collapse smoothly and coherently, forming a black hole of perhaps 100,000 solar masses in one dramatic implosion. Direct collapse black holes are an active area of research, and some models suggest they could explain the heavy seeds needed for supermassive black hole formation. But quasi-stars offer another pathway, one that's arguably more elegant, if more exotic. In the quasi-star scenario, the seed black hole forms at the centre of a massive gas envelope, and then grows rapidly through accretion. The quasi-star phase might last only a few million years, but during that time, the black hole could consume enormous amounts of material. When the envelope is finally exhausted, what remains is a black hole perhaps 100,000 times the mass of the Sun, heavy enough to grow into a supermassive black hole through normal processes over the subsequent billions of years. The appeal of quasi-stars is that they naturally produce heavy seeds, while also explaining other features of the early universe. The enormous luminosity of quasi-stars might have contributed to ionization, the process by which ultraviolet radiation from the first luminous sources ionized the neutral hydrogen that filled the early cosmos. The unique spectral signatures of quasi-stars might be detectable in deep observations of the distant universe, and the black hole remnants left behind might have specific properties, masses, spins, spatial distributions that could be tested against observations. There's also the intriguing possibility that quasi-stars and direct collapse black holes are related. Some models suggest that direct collapse might be the first stage of quasi-star formation. The initial black hole forms through direct collapse, and then the surrounding gas settles into the quasi-star configuration. In this view, quasi-stars are a natural consequence of direct collapse in the most massive gas clouds, adding an extra stage of black hole growth before the seed is fully released. Scholars continue to debate the relative importance of these different pathways. Some argue that direct collapse alone can explain the observed population of supermassive black holes. Others insist that quasi-stars are necessary to bridge the gap. The truth probably lies somewhere in between, a mix of mechanisms operating under different conditions, producing the diverse population of supermassive black holes we see scattered across the universe. One quirky aspect of this debate is its reliance on simulations. We can't observe the early universe directly. The light is too old, too faint, too red-shifted for easy interpretation. Instead, we build mathematical models and run them on supercomputers, simulating the formation and evolution of the first cosmic structures. These simulations are enormously complex, incorporating gravity, hydrodynamics, radiation transport, and nuclear physics, all operating across scales from individual atoms to entire galaxies. The results are suggestive but not conclusive. Different simulations using different assumptions and approximations produce different outcomes. Some find that quasi-stars form readily under the right conditions, others struggle to create them at all. The discrepancies reflect our incomplete understanding of the relevant physics, particularly in the extreme conditions of the early universe, where few of our assumptions have been tested. But despite the uncertainties, the basic picture is compelling. Supermassive black holes exist. They existed early in cosmic history. They needed seeds to grow from, and quasi-stars, those impossible, theoretical, rule-breaking monsters, might have been the nurseries where those seeds were planted. The universe, it seems, had to break a few rules to build itself. You've been drifting through theoretical space for a while now, so let's return briefly to the concrete world of observation. There's a telescope floating in space right now, about 1 million miles from Earth, peering back toward the beginning of time. It's called the James Webb Space Telescope, and it represents one of humanity's most ambitious attempts to understand where we came from. JWST launched in December 2021 after decades of development, delays, cost overruns, and engineering challenges that would make most project managers weep. It's the largest and most powerful space telescope ever built, with a primary mirror 6.5 meters across, more than 2.5 times the diameter of Hubble's. But its true power lies not in size, but in capability. JWST is optimized for infrared observation, allowing it to see light that has been stretched by cosmic expansion from visible wavelengths into the infrared. This infrared sensitivity is crucial for studying the early universe. when the first stars and galaxies formed, they emitted light across the electromagnetic spectrum, including plenty of visible light. But over the billions of years since, that light has been travelling through expanding space, and the expansion has stretched its wavelength. Light that started as blue or green or yellow has been shifted toward red, then into infrared, then into longer and longer wavelengths. By the time it reaches us, the most ancient light in the universe is invisible to optical telescopes like Hubble. Only infrared instruments can see it. JWST began its science operations in 2022, and the results have already been remarkable. It has detected galaxies at redshifts of 10, 11, even higher, meaning we're seeing them as they existed when the universe was only a few 100 million years old. Some of these early galaxies are unexpectedly bright and massive, challenging our models of how quickly cosmic structures could have formed. Others show signs of active star formation, their spectra rich with emission lines from ionized gas. The data is pouring in faster than astronomers can fully analyze it, each observation raising new questions even as it answers old ones. So what about quasi-stars? Can JWST detect them? The answer is maybe. In principle, quasi-stars would have been enormously luminous, easily bright enough to be detectable across cosmic distances. Their light would have been redshifted into exactly the infrared bands where JWST is most sensitive, and their spectra would show distinctive features, the signatures of pristine primordial gas, unlike anything found in later stellar populations. But in practice, detection is challenging. Quasi-stars, if they existed, were probably rare. The specific conditions required for their formation, massive primordial gas clouds, no heavy elements, the right balance between gravity and radiation pressure, would have been met in only a small fraction of the early universe. We might need to survey vast areas of sky to have a reasonable chance of finding even one. There's also the problem of identification. At the distances involved, even a quasi-star would appear as a point source, a tiny dot of infrared light indistinguishable by shape from a small galaxy or a very bright star. To identify it as a quasi-star, we would need detailed spectroscopy, breaking the light into its component wavelengths and analysing the chemical signatures. This requires long observation times and careful analysis, limiting the number of candidates we can examine. Nevertheless, the search is underway. Several research groups are combing through JWST data looking for unusual objects that might be quasi-stars or their descendants. They're particularly interested in sources that appear point-like, suggesting a compact object, show high luminosity, consistent with quasi-star brightness, and have spectra dominated by hydrogen and helium, indicating primordial composition. It's a needle in a haystack problem, but the haystack is smaller than you might think. JWST's deep field observations contain only thousands of sources, not millions, making systematic examination feasible. One intriguing possibility is that JWST has already observed quasi-stars without knowing it. Among the unexpectedly bright sources in the early universe, some might be quasi-stars masquerading as small galaxies. The distinction would require spectroscopic follow-up to determine something that hasn't been done for most of the newly discovered objects. As JWST continues its mission and follow-up observations accumulate, we might find that some of those bright early sources turn out to be something much more exotic than initially assumed. There's also hope from gravitational lensing. When light from a distant source passes near a massive intervening object, a galaxy or galaxy cluster, it can be bent and magnified, acting like a cosmic zoom lens. Some of the most distant objects we've observed have been found because they happen to be aligned with such lensing systems, their light amplified by factors of 10 or 100. A quasi-star that would otherwise be too faint to detect might become visible if it's fortuitously positioned behind a suitable lens. Astronomers are actively searching for such lens sources in JWST data. The statistics suggest that we should find some. The universe is full of gravitational lenses, and the most distant sources have the highest probability of being lensed. Whether any of those lens sources turn out to be quasi-stars remains to be seen. Scholars debate the likelihood of detection with their usual mix of optimism and caution. Some models predict that JWST should find quasi-stars within its first few years of operation. Others suggest we might need to wait for even more powerful future telescopes. The uncertainty reflects our incomplete understanding of both quasi-star physics and early universe conditions. We won't know until we've looked, and even then, a null result won't conclusively disprove quasi-stars. It might just mean they were rarer than we hoped. The search continues. Somewhere in the infrared glow of the early universe, encoded in patterns of ancient photons, there might be evidence of monsters. Not everyone believes in quasi-stars. That might seem surprising given how elegantly they solve the supermassive black hole seed problem, but science thrives on skepticism, and there are plenty of researchers who think the quasi-star hypothesis is unnecessary, unlikely, or simply wrong. Let's give the skeptics their due. The most fundamental criticism is one of parsimony. Why invoke an exotic, never-observed object when simpler explanations might suffice? Direct collapse black holes, for instance, don't require the quasi-star intermediate stage. If conditions allow a massive gas cloud to collapse directly into a black hole of 100,000 solar masses, then you've got your heavy seed without needing to postulate a star-like envelope around it. The direct collapse pathway is simpler, requires fewer assumptions, and might be more common than quasi-star formation. Why add complexity when Occam's razor suggests otherwise? Proponents of quasi-stars counter that direct collapse and quasi-star formation might be the same process viewed at different stages. A direct collapse black hole doesn't form instantaneously. The gas has to fall inward over time, and during that process the system might pass through a quasi-star-like configuration. In this view, quasi-stars aren't an alternative to direct collapse. They're a natural consequence of it. The debate then becomes about timescales and observational signatures rather than fundamental physics. Another line of criticism concerns the stability of quasi-stars. The models assume that the enormous gas envelope can remain in hydrostatic equilibrium while a black hole feeds at its centre, but this equilibrium might be more fragile than the models suggest. Real astrophysical systems are messy. They experience turbulence, magnetic fields, angular momentum transport, and other phenomena that are difficult to capture in simplified models. A quasi-star might form briefly but then rapidly destabilize, its envelope either collapsing into the black hole or being expelled in violent outbursts. The millions of years lifetimes that some models predict might be wildly optimistic. Scholars who favour this view point to analogous systems in the modern universe. When black holes accrete material rapidly, they often produce powerful jets and winds that can blow away the surrounding gas. Quasars, powered by supermassive black holes consuming material at near Eddington rates, are famous for their energetic outflows. If quasi-stars experience similar feedback, their envelopes might be disrupted long before the black hole had time to grow substantially. The seed produced would be smaller than predicted, reducing the advantage of the quasi-star pathway. Then there's the question of initial conditions. Quasi-star formation requires very specific circumstances: massive gas clouds, primordial composition, the right temperature and density profiles. How common were such conditions in the early universe? Different models give different answers, and the uncertainty is large. If quasi-star formation was exceedingly rare, if only 1 in a million suitable gas clouds actually produced a quasi-star, then they might not have been common enough to explain the observed population of supermassive black holes. Other mechanisms would have to dominate. Some researchers propose alternative heavy seed sources entirely. Primordial black holes, for instance, might have formed in the first moments after the Big Bang through exotic physics, unrelated to stellar processes. These primordial black holes could have served as seeds for supermassive black holes, without requiring any stellar or quasi-stellar intermediate. The primordial black hole hypothesis has its own problems and uncertainties, but it illustrates that the space of possible explanations is broader than just quasi-stars versus standard stellar remnants. Another alternative is the runaway merger scenario. In dense stellar environments, perhaps the cores of early galaxies or star clusters, massive stars might have collided and merged repeatedly, building up objects of hundreds or thousands of solar masses. These supermassive stars would have been unstable, eventually collapsing into black holes much heavier than normal stellar remnants. Subsequent mergers of these intermediate mass black holes could have produced the seeds for supermassive black holes. This pathway doesn't require quasi-stars at all, just unusually dense stellar environments in the early universe. The honest truth is that we don't know which mechanism dominated, or even if a single mechanism was responsible. The early universe was a big place, with diverse environments and conditions. Different pathways to supermassive black holes might have operated in different regions, producing the varied population we observe today. Quasi-stars might have been one contributor among several, important in some contexts but not universal. This kind of pluralism is common in astrophysics. We rarely find that a single explanation accounts for all observations. Instead, we find families of mechanisms operating across a range of conditions, each dominant in its own domain. The formation of supermassive black holes is probably no different, a complex process with multiple pathways, not a simple story with a single protagonist. What keeps the quasi-star hypothesis alive despite the skepticism is its theoretical elegance and its ability to solve a real problem. The rapid growth of supermassive black holes in the early universe does need explanation. Heavy seeds are required, whatever their source, and quasi-stars provide a natural, physically motivated pathway to producing those seeds. Until we have direct observational evidence one way or another, the hypothesis remains viable, a theoretical ghost that might yet prove to be real. The debate continues in academic journals and conference halls, in simulations running on supercomputers and observations streaming from space telescopes. Each piece of new data refines our understanding, nudging probabilities one way or another. Science moves slowly but relentlessly, and eventually, perhaps not in our lifetimes, but eventually, we'll know. For now, quasi-stars remain in that liminal category. Possible, plausible, unproven. Ghosts at the edge of physics, waiting to be conjured into reality or dismissed into oblivion. And with that thought, let us slow down. Let the technical debates fade into background murmur. Let the equations and simulations retreat to their whiteboards and servers. You've travelled far tonight, through the physics of stellar structure, through the darkness of the early universe, through the theoretical machinery of quasi-star formation. You've learned about objects that might never have existed, seen by nobody, leaving traces we may never find. That's a lot to carry, so let your breathing deepen. Let your thoughts grow soft and diffuse, like the outer envelope of a quasi-star spreading across billions of kilometres. The universe is vast and strange and old beyond imagining, but right now, in this moment, you are here, warm and safe, wrapped in familiar darkness, drifting towards sleep. The monsters are far away, if they exist at all. The questions will still be there tomorrow. Tonight, you can rest. Feel the weight of your body settling into whatever surface supports you. Notice the gentle rhythm of your breath, in and out, like the slow pulsing of distant stars. The cosmos turns overhead, indifferent and magnificent, but you don't have to watch it anymore. You've done enough watching for one night. Now it's time to close your eyes and let the darkness be a comfort rather than a mystery. Let the quasi-stars fade into the ancient past where they belong. Let the supermassive black holes spin in their galactic cores, too far away to trouble your dreams. Let everything be distant and peaceful and still. The light from the early universe will keep travelling while you sleep. It's been travelling for 13 billion years already. It can manage one more night. And when you wake, the stars will still be there. Some burning bright, some long dead, all of them part of the same grand story that includes you. You, with your small life and your brief span and your beautiful, improbable consciousness. here to wonder at things you can never fully understand. That's enough. That's more than enough. So rest now. Let the cosmic monsters keep their secrets. Tomorrow is another day to be curious. Tonight is for sleep. Breathe in, breathe out, and drift. But the universe, it turns out, has more than one type of monster. Quasi-stars may be the most extreme theoretical objects, hidden black holes wearing stellar disguises, but they're hardly alone in the cosmic bestiary. The night sky, if you could see it properly, is full of rule breakers. Objects that spin too fast, shine too bright, or explode with too much violence for comfortable comprehension. Let's spend some time with these other cosmic auditors, because they remind us that the universe has never been particularly interested in our definitions of what's possible. Consider the magnetar. This is a type of neutron star, the ultra-dense remnant left behind when a massive star explodes as a supernova. Neutron stars are already strange objects. Imagine something with the mass of the Sun compressed into a sphere about 20 kilometers across, roughly the size of a city. A teaspoon of neutron star material would weigh about 6 billion tons. The surface gravity is so intense that if you somehow stood on a neutron star, you couldn't, but hypothetically, you would be flattened to a thickness of a few atoms before you had time to register what was happening. But magnetars take this strangeness and amplify it enormously. They are neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. Fields so powerful they would erase your credit card from halfway across the solar system if credit cards could somehow exist in that environment. The magnetic field of a magnetar contains more energy than the Sun will produce in the next several thousand years. It warps the structure of the star itself, creating mountains perhaps a millimeter high, which, given the absurd gravity, represents an almost unimaginable concentration of force. The discovery of magnetars came gradually through the 1990s and 2000s as astronomers detected bursts of X-rays and gamma rays from certain neutron stars that couldn't be explained by normal rotational energy. Regular pulsars, spinning neutron stars that sweep beams of radiation across the sky like cosmic lighthouses, slow down over time as they radiate away their rotational energy. But magnetars could produce enormous energy bursts even when spinning relatively slowly. The energy had to come from somewhere, and the most plausible source was the decay of their extraordinary magnetic fields. In 2004, a magnetar called SGR 1806-20 produced a burst of energy so intense that it literally ionized Earth's upper atmosphere from 50,000 light-years away. If the same burst had occurred from a typical stellar distance of a few light-years, it would have sterilized our planet entirely. We were lucky. The universe, it seems, occasionally throws punches that could end civilizations, and we only survive because of the cosmic distances that separate us from the most violent phenomena. Then there are the pulsars themselves, spinning neutron stars that emit beams of radiation from their magnetic poles. When these beams sweep across Earth, we detect regular pulses of radio waves, sometimes accompanied by X-rays or gamma rays. The precision of pulsar timing is extraordinary. Some millisecond pulsars are more accurate than atomic clocks, their rotation rate stable to fractions of a second over billions of years. Scientists use pulsars as cosmic timekeepers, detecting subtle variations in their timing that reveal passing gravitational waves, orbiting planets, or other perturbing influences. The fastest known pulsar spins at about 716 times per second. Let that sink in. An object with the mass of the Sun, compressed to 20 kilometers across, rotating faster than a kitchen blender. At its equator, the surface is moving at roughly a quarter of the speed of light. Any loose material would be flung off instantly by centrifugal force. The star is a blur, a smeared disk of spinning nuclear matter, held together only by gravity so strong it makes Earth's pull look like a gentle breeze. How do pulsars spin so fast? The standard explanation is accretion. When a neutron star has a companion, another star orbiting nearby, it can gravitationally strip material from that companion. As the material falls onto the neutron star, it transfers angular momentum, spinning the neutron star up like a figure skater pulling in their arms. Over millions of years of accretion, a slowly rotating neutron star can be accelerated to millisecond periods. These recycled pulsars represent some of the most extreme rotational velocities in the universe. Astronomers still debate some aspects of pulsar physics. The exact mechanism that produces the radio emission, for instance, remains somewhat mysterious. The emission appears to come from regions above the magnetic poles, where charged particles are accelerated to relativistic speeds and radiate coherent radio waves. But the details of this process, how the particles are accelerated, how the coherent emission is produced, why some pulsars emit and others don't, are active areas of research with competing models. There's also the question of what happens at the very end of a neutron star's life. Do they eventually cool to invisibility? Do they merge with companions and produce black holes? Do some of them undergo exotic phase transitions in their cores, transforming into even stranger objects? The possibilities multiply as you dig deeper, revealing ever more exotic corners of physics. One particularly intriguing possibility is that some neutron stars might not be neutron stars at all. Under sufficient pressure, even neutrons can break down into their constituent quarks. A quark star, if such things exist, would be even denser than a neutron star, composed of a soup of up, down, and strange quarks in a new phase of matter never observed in laboratories. We'll talk more about these hypothetical objects later. For now, it's enough to note that neutron stars themselves might just be one stage in a progression toward even more extreme states of matter. The universe, as we're discovering, has a vast imagination. Every time we think we've found the strangest possible object, something stranger lurks just beyond our current understanding. Quasi-stars were our main focus tonight, but they exist in a context, a cosmic zoo of peculiar beasts, each pushing the boundaries of what physics allows. Let the strangeness wash over you. Let it be wonder rather than worry. The universe is wild, yes, but it's also far away, and your bed is soft and the night is long. These monsters can keep each other company while you rest. Picture this. You're standing on a small planet, one that somehow exists in a safe orbit around a very normal star. The sky above you looks much like Earth's sky. A scattering of stars, a band of galactic light stretching from horizon to horizon, the usual cosmic backdrop that our species has gazed upon for millennia. And then, one day, something changes. A new star appears where none existed before, growing brighter and brighter until it outshines everything else in the sky. Within days, it's visible during daylight. Within weeks, it's brighter than your sun. And then you realize it's not actually a star at all. It's the energetic jet of a supermassive black hole pointed directly at your planet. This is a blazar. The name sounds almost playful, like some kind of fictional weapon, but blazars are very real and very terrifying. They occur when the supermassive black hole at the center of a galaxy is actively accreting matter, producing intense radiation and powerful jets of plasma that stream outward at nearly the speed of light. Most of the time, these jets point off into space at various angles, affecting nothing in particular. But occasionally, through cosmic coincidence, a jet points almost directly at Earth. When that happens, we see a blazar, one of the most energetic, sustained phenomena in the universe. The first blazar was identified in the 1960s, though astronomers didn't understand what they were seeing at the time. An object called BL Lacertae, literally in the lizard constellation, showed peculiar properties. It varied in brightness rapidly and irregularly. Its spectrum was featureless and strange, and it appeared point-like even in the most powerful telescopes. For years, it was classified as an unusual variable star. Only later did astronomers realize they were looking almost straight down the barrel of a relativistic jet. When material falls toward a black hole, it doesn't simply drop in. It spirals inward through an accretion disk, heating up through friction and releasing enormous amounts of energy. Some of this energy escapes as radiation. Some is channeled into magnetic fields that twist and concentrate near the black hole's poles. Under the right conditions, these magnetic fields can launch jets of plasma, material accelerated to 99.9% of the speed of light or faster, streaming outward in narrow beams that can extend for millions of light years. These jets are one of the most powerful sustained phenomena in the universe. The energy they carry is staggering, in some cases equivalent to converting entire stars into pure radiation every year. They punch through the interstellar medium, sweep aside gas clouds, and deposit enormous amounts of energy into the galaxies that host them. In extreme cases, they can actually regulate the growth of the galaxy itself, heating the surrounding gas and preventing new stars from forming. When we happen to be aligned with one of these jets, the effects are amplified by relativistic beaming. Because the material in the jet is moving toward us at nearly the speed of light, the radiation it emits is boosted in intensity and shifted toward higher frequencies. What would be a moderately bright object viewed from the side becomes a blazingly luminous beacon viewed head-on. This is why blazars can outshine their host galaxies by factors of thousands, despite being powered by the same accretion processes that produce more modest active galactic nuclei. The variability of blazars is one of their most distinctive features. Unlike stable stars, which shine with constant luminosity, blazars can change brightness dramatically over days, hours, or even minutes. This variability tells us something about the structure of the emitting region. It must be small, since large objects can't change coherently on short timescales. The light we see from a blazar comes from a region perhaps the size of our solar system, tiny by galactic standards, where the jet is most concentrated and most energetic. There's something deeply unsettling about blazars, even though the nearest ones are safely far away. They represent the universe's capacity for focused destruction, for channeling unimaginable energy into narrow beams that slice through space. If a blazar jet were pointed at Earth from a nearby galaxy, even tens of millions of light years away, the consequences could be severe. The radiation could damage our atmosphere, trigger mass extinctions, perhaps even sterilize the entire biosphere. We're lucky that no such alignment exists. Astronomers have identified thousands of blazars across the sky, mostly through surveys at radio, X-ray and gamma-ray wavelengths. Some are relatively nearby, in galaxies only a few hundred million light-years distant. Others are at the edge of the observable universe, their light travelling for billions of years to reach us. By studying blazars at different distances, we can trace the evolution of active galactic nuclei over cosmic history, learning how black holes grew, how jets formed, and how these processes shape the galaxies we see today. One quirky detail: the jets from active galactic nuclei can sometimes create structures called radio lobes, enormous bubbles of magnetized plasma inflated by the jet and extending far beyond the visible galaxy. The largest of these structures are millions of light years across, among the biggest coherent objects in the universe. They glow at radio wavelengths, revealing the history of jet activity over millions of years. When you look at images of radio galaxies, you're seeing the fossilized evidence of ancient cosmic violence, the scars left by jets that may have shut off millions of years ago. Scholars debate many aspects of blazar physics. The exact mechanism that collimates the jets, keeping them narrow and focused over such vast distances, is still not fully understood. The composition of the jets, whether they're made primarily of electrons and positrons, or include heavier particles like protons, remains uncertain. The connection between jet power and black hole mass spin and accretion rate is an active area of research. We know broadly what blazars are, but the details continue to surprise and challenge us. The universe, it seems, has many ways of being dangerous. Quasi-Stars threatened through their sheer size and the black holes they nurtured. Magnetars threaten through magnetic fields that defy comprehension, and blazars threaten through focused beams of energy that could, in principle, reach across cosmic distances to wreak havoc on unsuspecting worlds. We're surrounded by cosmic monsters, kept safe only by the vast emptiness of space, a comforting thought in its way. The emptiness that sometimes makes us feel lonely is also what protects us from the violence that pervades the cosmos. Let's venture now into territory even more speculative. Objects that might exist, probably exist, but have never been conclusively observed. If quasi-stars are ghosts from the past, these are phantoms from the present, hiding in plain sight or lurking at the edges of our detection capabilities. Start with strange stars. The name sounds like something from a children's book, but the physics behind them is anything but whimsical. A strange star would be a type of compact object similar to a neutron star but composed of different material, specifically something called strange quark matter. Ordinary matter is made of protons and neutrons, which in turn are made of up and down quarks bound together by the strong nuclear force. Under normal conditions, quarks are always confined inside protons and neutrons. You can't isolate a single quark. But under extreme pressures, the kind found in the cores of neutron stars, the boundaries between individual nucleons might break down. The quarks would merge into a continuous soup, a new phase of matter never seen in laboratories. If this quark soup includes roughly equal numbers of up, down, and strange quarks, it's called strange quark matter. And here's the truly bizarre part. According to some theoretical models, strange quark matter might be more stable than ordinary nuclear matter. If that's true, then neutron stars might actually convert to strange stars under the right conditions, their neutrons dissolving into quark soup that represents a lower energy state. A strange star would look from the outside much like a neutron star. It would have similar mass and size, similar surface gravity, similar ability to produce radio pulses and X-ray emission. The differences would be subtle, slight variations in mass-radius relationships, different cooling rates, perhaps distinctive features in gravitational wave signals. So far, we haven't been able to distinguish any known object as definitively a strange star rather than a neutron star. The evidence remains circumstantial and contested. Some researchers have proposed that strange stars might explain certain puzzling observations. A few compact objects have been identified with masses and radii that don't quite fit standard neutron star models. Others have been observed with surface temperatures that cool faster than expected. Could these anomalies indicate strange quark matter? Possibly. Or they could indicate gaps in our understanding of ordinary nuclear physics under extreme conditions. The debate continues. There's also the tantalizing possibility that strange quark matter could be absolutely stable, more stable than iron, the most stable element in ordinary nuclear physics. If that's true, then any ordinary matter that comes into contact with strange quark matter would convert, releasing energy and propagating the transformation. A strange star crashing into a planet would potentially convert the entire planet into strange matter. A lump of strange matter passing through the sun could seed a conversion that would remake our entire star. This sounds alarming, and science fiction authors have certainly exploited the apocalyptic potential. But there's a simple reason not to worry. If strange matter were that dangerously contagious, it would have already converted everything. The universe is old, and violent events that could produce strange matter have been happening for billions of years. The fact that ordinary matter still exists suggests that either strange matter isn't stable, or the conversion process is somehow inhibited. We can sleep soundly on that particular nightmare. Now consider an even more exotic possibility. Dark stars. Not black holes, something fundamentally different. The theory of dark stars emerged from attempts to understand what the universe might have been like in its very earliest moments, when dark matter dominated even more completely than it does today. Dark matter is one of the great mysteries of modern physics. We know it exists because we can see its gravitational effects. It holds galaxies together, bends light from distant sources, shapes the large-scale structure of the cosmos. But we don't know what it's made of. Dark matter doesn't emit light, doesn't absorb light, doesn't interact with ordinary matter except through gravity. It's invisible, intangible, and utterly pervasive. Most dark matter theories assume it's made of some kind of particle, WIMPs, weakly interacting massive particles, axions, or something even more exotic. These particles would barely interact with each other, drifting through the universe as a diffuse background. But some models allow for dark matter self-interactions, including dark matter annihilation, when two dark matter particles collide and convert their mass into energy. In the early universe, when dark matter densities were higher than today, this annihilation could have been significant. And in the cores of the first protostars, gas clouds collapsing to form the first stars, dark matter might have accumulated in sufficient quantities to power the star through annihilation rather than nuclear fusion. These objects would be dark stars, luminous, not because of hydrogen fusing into helium, but because of dark matter converting into radiation. Dark stars would have been enormous, potentially thousands of times larger than the Sun, and incredibly massive, perhaps millions of solar masses. They would have burned relatively cool, like quasi-stars, their huge surface areas spreading the luminosity across vast extents. And when the dark matter fuel was exhausted, when the annihilation rate dropped below what was needed to support the star, they might have collapsed directly into supermassive black holes. Sound familiar? Dark stars occupy similar theoretical territory to quasi-stars, offering another pathway to early supermassive black hole formation. The key difference is the energy source: dark matter annihilation rather than accretion onto a central black hole. Both mechanisms could have operated, perhaps in different environments or at different times. The early universe might have hosted both quasi-stars and dark stars, along with more conventional massive stars and direct collapse black holes. Whether dark stars actually existed depends on dark matter physics that we don't yet understand. If dark matter annihilation is efficient enough, and if dark matter accumulated sufficiently in early protostars, then dark stars were possible. If not, they remain purely theoretical, interesting mathematical constructs with no physical realization. Current observations can't distinguish between these possibilities, though future telescopes and dark matter experiments might provide constraints. The universe's zoo of hypothetical objects is vast. Strange stars, dark stars, quark stars, preon stars, each represents a different corner of theoretical physics, a different set of assumptions about how matter behaves under extreme conditions. Some of these objects probably exist, others probably don't. Figuring out which is the work of generations of scientists, slowly narrowing the possibilities through observation and experiment. For now, they remain phantoms. Fascinating, plausible, unproven phantoms. We've talked about objects that are enormous, objects that are dense, objects that are powered by black holes or dark matter or magnetic fields of unimaginable strength. But there's another category of cosmic monster worth considering: objects that are invisible. Not because they're far away or faint, but because they don't emit any detectable radiation at all. They exist, they have mass, they affect their surroundings, but they hide in plain darkness. The most familiar example is the black hole itself. Black holes don't emit light by definition. Their gravity is so strong that nothing, not photons, not matter, not information, can escape once it crosses the event horizon. When we see a black hole, we're actually seeing the effects of its gravity on surrounding material. The glow of an accretion disk, the lensing of background light, the motion of stars orbiting an invisible massive object. The black hole itself remains forever hidden, revealed only by its influence on everything around it. But black holes aren't the only invisible giants. Consider rogue planets. Planets that have been ejected from their parent star systems and now wander through interstellar space, bound to no star, lit by no nearby sun. Rogue planets are probably extremely common. Computer simulations of planetary system formation suggest that the gravitational chaos of early solar systems ejects far more planets than are retained. For every planet happily orbiting a star, there might be dozens of rogues drifting through the darkness. Our own solar system probably ejected several planet-sized bodies during its chaotic youth, and similar processes would have occurred around every other star that formed planets. These rogue planets would be essentially invisible. Without a nearby star to illuminate them, they would emit only the faint infrared glow of their internal heat. Warmth left over from their formation, slowly radiating into space. A Jupiter-sized rogue planet would be almost undetectable at interstellar distances, a dark mass drifting through the void with no way to announce its presence. Some rogue planets might retain atmospheres or even oceans kept liquid by internal heat sources. A planet with active geology, tidal heating from a captured moon, perhaps, or radioactive decay in its core could potentially maintain habitable conditions on its surface or in subsurface oceans, even without any input from a star. Life on such a world would never see starlight, would have no concept of day and night, would exist in eternal darkness warmed only from below. We've detected a handful of rogue planets through gravitational microlensing, events where a rogue planet passes between us and a distant star, briefly magnifying the star's light through gravitational effects. These detections are rare and serendipitous, revealing only a tiny fraction of the rogue planet population. The true number is unknown, but estimates range from billions to trillions in our galaxy alone. A vast unseen population drifting through the darkness between stars. Then there are primordial black holes, hypothetical black holes that might have formed in the earliest moments of the universe, before stars or galaxies existed. The physics of primordial black hole formation is different from stellar mass black holes. Instead of forming from collapsing stars, primordial black holes would have formed from density fluctuations in the early universe, regions where matter was concentrated enough to collapse directly into black holes before anything else had time to form. Primordial black holes could span an enormous range of masses. Some might be tiny, smaller than an atom, less massive than an asteroid, and would have evaporated long ago through Hawking radiation. Others might be substantial, planetary masses, stellar masses, or even heavier, and would still exist today, drifting invisibly through space. If primordial black holes exist in sufficient numbers, they could constitute some fraction of dark matter, explaining the gravitational effects we observe without requiring exotic new particles. The evidence for primordial black holes is currently inconclusive. Various observations constrain their abundance in different mass ranges, but significant windows remain open. Gravitational wave detections from LIGO and Virgo have revealed black hole mergers with masses that don't quite fit standard stellar evolution models. Could some of these be primordial black holes? The question remains open. There's a strange poetry to invisible objects. We navigate our lives surrounded by things we can see, touch, hear. Our senses evolve to perceive the world immediately around us, the savanna and the forest, and the faces of our companions. But the universe is mostly invisible. Dark matter pervades every galaxy. Rogue planets outnumber stars. Black holes lurk unseen, their presence revealed only through inference and gravitational whispers. The darkness isn't empty, it's full of mass and mystery, objects that interact gravitationally with everything around them while emitting not a single photon for us to catch. When you look up at the night sky and see stars, you're seeing only a fraction of what's there. The rest is hidden, dark, known only through its effects. There's something humbling about this. Our vision, so seemingly comprehensive, actually reveals only a thin slice of reality. The universe has depths we can barely glimpse, structures we can barely detect, objects we can barely imagine. Quasi-stars, strange stars, dark stars, rogue planets, primordial black holes. Each represents a different way for the cosmos to be invisible. to hide in plain darkness while still shaping the evolution of everything around it. And yet we persist in looking. We build telescopes and gravitational wave detectors and particle colliders, extending our senses into domains they were never evolved to perceive. We infer the existence of objects we cannot see, deduce the properties of matter we cannot touch. This is perhaps the strangest thing of all. Creatures of light, evolved under a yellow sun, reaching out to comprehend the darkness that surrounds us. The search continues. The invisible objects keep their secrets, and somewhere in the vast, dark spaces between stars, cosmic monsters drift silently on, waiting to be discovered. Let's slow down now. Let the data and the theories and the cosmic violence recede a bit. You've travelled far tonight, through the physics of quasi-stars, through the menagerie of cosmic monsters, through objects visible and invisible, possible and impossible. Your mind has stretched across billions of light years and billions of years, touching things that no human will ever experience firsthand. That's a lot. Let's take a breath. There's a philosophical dimension to all of this that we haven't really addressed. What does it mean that the universe produces such objects? What does it mean that we, small creatures on a small planet, can deduce their existence from fragments of light and mathematical inference? What does it say about reality, about consciousness, about the strange fact that anything exists at all? These questions don't have scientific answers, strictly speaking. Science tells us how the universe works, not why it exists or what it means, but they're worth pondering, especially late at night when the boundary between intellectual understanding and emotional experience grows thin. Consider the sheer extravagance of creation. The universe didn't have to be this way. It could have been simpler, containing only hydrogen atoms drifting forever in an infinite void. It could have been more complex, with additional forces and particles and dimensions that we can barely imagine. Instead, we got this. A cosmos that allows stars and planets and black holes and life. A cosmos where complexity emerges naturally from simple rules, where 13 billion years of evolution can produce creatures capable of wondering why they exist. Quasi-stars, if they existed, were part of this extravagance. They weren't necessary for anything. The universe would have gotten along fine without them. But the same laws that allow planets and people also allow objects of terrifying extremity, stars with black holes for hearts, cosmic monsters that violate the limits we thought were absolute. The universe is permissive. It allows almost anything that doesn't violate fundamental conservation laws, and it explores these possibilities with an enthusiasm that borders on reckless. This extravagance extends in both directions, toward the enormous and toward the tiny. Quasi-stars might have been millions of solar masses. Quarks are a billion times smaller than a human hair. The range of scales in the universe spans roughly 60 orders of magnitude, from the smallest meaningful length, the Planck scale, to the largest observable distances, the cosmic horizon. And at every scale, interesting things happen. Particles interact, atoms combine, molecules fold, cells divide, organisms evolve, stars burn, galaxies spiral, clusters form. The universe is not just large, it's deep, with structure nested within structure at every level of magnification. Human beings exist somewhere in the middle of this vast range. We're about midway between atoms and stars, roughly equidistant from the Planck scale and the cosmic horizon. Some physicists have speculated that this is not coincidental, that observers like us can only exist at scales where certain kinds of complexity are possible. Too small, and there isn't enough room for the intricate machinery of life. Too large, and gravitational effects dominate everything else. We occupy a sweet spot, a Goldilocks zone of scale where chemistry and biology can flourish. But even if our size is somehow necessary for our existence, that doesn't diminish the strangeness of our position. We're caught between extremes we can barely comprehend. The quantum fuzziness of subatomic particles, the gravitational depths of black holes. We use instruments to extend our senses, mathematics to extend our intuitions, language to communicate what we've found. And still, the universe exceeds our grasp. There's always more to discover, more to understand, more to wonder at. The cosmic monsters we've discussed tonight are part of this wonder. They represent the universe's willingness to explore extreme configurations of matter and energy, to push against limits and see what happens. Quasi-stars are nature's experiment in combining stellar and black hole physics. Magnetars are nature's experiment in extreme magnetism. Blazars are nature's experiment in focused relativistic energy. Each object teaches us something about the range of physical possibility, about what the laws of nature allow and forbid. There's comfort in this if you look for it. The universe is not arbitrary. It follows rules, even when those rules permit extraordinary outcomes. The same physics that explains the behavior of everyday objects, the warmth of sunlight, the flow of water, the beating of your heart, also explains the existence of quasi-stars and black holes and neutron stars. We're connected to those distant extremes by the same fundamental forces, the same mathematical structures. The cosmos is one thing, not many, and we're part of it. And here's the final philosophical point. The fact that we can understand any of this is itself remarkable. Human brains evolved to navigate African savannas, to track prey, to find mates, to avoid predators. They were not designed for astrophysics. And yet, somehow, the same cognitive capacities that helped our ancestors survive also allow us to comprehend the structure of the cosmos. We can write equations that describe black holes. We can build telescopes that see the early universe. We can imagine objects that no human will ever observe directly. This suggests something profound about the relationship between mind and cosmos. The universe is comprehensible, at least in part. The mathematics we invent to describe our immediate surroundings also describes phenomena billions of light years away. There's a resonance between the structure of reality and the structure of thought, a harmony that allows understanding to occur. Why this should be so is one of the deepest mysteries of all. Perhaps it's just a coincidence. Evolution happened to produce brains that can do physics, and we got lucky. Perhaps there's something deeper going on, some principle we haven't yet discovered that explains why the universe is comprehensible to minds like ours. We don't know. We may never know. But the mystery itself is worth savouring, especially on nights like this, when the stars are out and the questions feel urgent. Breathe in, breathe out. Let the wonder settle. The universe is vast and strange and old, but you're here, now, thinking about it. That's a kind of miracle too. Here's an odd comfort. Your smallness doesn't matter as much as you might think. Or rather, it matters in ways that are different from the anxious implications we often draw from it. When people contemplate the scale of the universe, the billions of galaxies, the trillions of stars, the incomprehensible distances, they often feel diminished. What are we, they ask, in the face of such immensity? We're specks on a speck, brief flickers in an eternal darkness. Our lives are so short, our reach so limited. The universe was here before us and will continue long after we're gone. In the grand cosmic scheme, we're nothing. This response is understandable. It's also, I think, slightly mistaken. It confuses spatial and temporal scale with value and significance. It assumes that bigger is somehow better, that lasting longer makes something more important. But these assumptions don't hold up under scrutiny. Consider, a quasar is enormously larger and longer lived than a human being. But is a quasar more significant? More valuable? By what standard? A quasar doesn't think, doesn't feel, doesn't wonder about its own existence. It's an impressive physical phenomenon, certainly, but it lacks the one thing that makes human life distinctive: consciousness. The ability to experience the world, to reflect on that experience, to wonder and hope and fear and love. The universe is full of objects that dwarf us in scale. Quasi-stars, if they existed, were millions of times more massive than our entire planet. Supermassive black holes contain billions of solar masses. The The observable universe spans 93 billion light-years, and yet, as far as we know, none of these objects can appreciate their own existence. None of them can look up at the stars and feel awe. None of them can write poetry or compose symphonies or tell jokes. Only we can do that. We, and perhaps other conscious beings scattered through the cosmos, if any exist. This isn't anthropocentric arrogance. It's a recognition that consciousness changes everything. A universe without observers is just a collection of events happening to no one. A universe with observers is a place where meaning can exist, where beauty can be appreciated, where questions can be asked. The presence of minds, even small, brief, limited minds like ours, transforms the cosmos from a mere mechanism into something like a story. And here's another thought. Our smallness is also our freedom. We're not enslaved to cosmic forces the way stars are. We're not trapped by gravity or magnetism, or the relentless conversion of mass into energy. We can choose what to do with our brief time. We can decide what matters to us, what to pursue, what to create. The universe doesn't care about our choices, but that's precisely what makes them ours. We're free precisely because we're insignificant by cosmic standards. There's a tradition in philosophy that finds liberation in recognizing our cosmic insignificance. The Stoics practiced it, contemplating the vastness of space and time as a way of freeing themselves from petty anxieties. The existentialists practiced it, finding in absurdity a kind of freedom from inherited meanings. The Buddhists practiced it, recognizing the transience of all phenomena as a path to letting go. Different traditions, different approaches, but a common thread. Our smallness, properly understood, can be a doorway to peace rather than despair. Tonight, as you drift towards sleep, you might try an experiment. Instead of letting the cosmic scale make you anxious, let it make you light. All those worries about tomorrow, the deadlines, the conflicts, the uncertainties, how do they look from 1 billion light-years away? How much will they matter in 1 million years? The universe has been here for 14 billion years and will continue for trillions more. In that vast span, your current concerns are barely a blip. That's not a reason to despair. It's a reason to relax. The pressure you feel is largely self-imposed. You could let it go. This doesn't mean nothing matters. It means that what matters is determined by you, not by cosmic scale. The love you feel for family and friends matters because you decide it matters. The work you do matters because you give it meaning. The moments of beauty and connection and joy matter because you experience them as meaningful. The universe doesn't assign these values. You do. And that's what makes them real. More real in their way than any quasi-star. The cosmic monsters we've discussed tonight are impressive. They represent extremes of physical possibility, natural experiments in what the universe allows. But they're not more important than you are. They're not more significant, they're just bigger, which is a different thing entirely. Size is a quantity, not a quality. Mass is a measurement, not a meaning. So let the quasi-stars be big. Let the black holes be massive. Let the universe span its 93 billion light-years and its 14 billion years. None of that diminishes the reality of your experience right now, your breath, your thoughts, your gradual drift towards sleep. You're a conscious being in an unconscious universe, a brief flicker of awareness in an otherwise dark cosmos. That's not insignificance. That's a kind of miracle. And with that thought, let the philosophical musings fade. Let the big questions recede into the background, where they can simmer quietly until the next time you're ready to contemplate them. For now, the journey is almost complete. The cosmic monsters have had their say. The universe has revealed some of its strangeness. What remains is the gentle descent into sleep, the soft landing after a long voyage through space and time. Breathe, rest. The stars will still be there tomorrow. You've been on quite a journey tonight. From that grassy field where you first tilted your head back to gaze at the stars, you've travelled to the edges of physics and the beginnings of time. You've encountered quasi-stars, those impossible objects with black holes for hearts, burning briefly in the cosmic dawn before vanishing into history. You've met magnetars and pulsars, blazars and strange stars, rogue planets and primordial black holes. You've contemplated the philosophical weight of cosmic monsters and found, perhaps, a kind of peace in your own smallness. Now it's time to come home. Feel the surface beneath you, the mattress, the couch, wherever you've made your nest for tonight. Feel how it supports your body, how your weight is distributed across it, how gravity gently holds you in place. This is your planet, your home, the one place in all the universe where you belong. Out there, among the stars, quasi-stars may have blazed and died. Supermassive black holes may be slowly consuming their galaxies. Magnetars may be warping space-time with fields of unimaginable strength. But here, in your small corner of reality, everything is quiet and safe. Notice your breathing. It's probably slower now than when we began, deeper and more regular. Each inhale brings oxygen to your blood. Each exhale releases what your body no longer needs. This rhythm has been with you since birth, will continue until death, a constant companion through every experience of your life. It requires no thought, no effort. It simply happens, carrying you along. The darkness around you is not the darkness between stars. It's not the primordial void where quasi-stars first ignited, nor the emptiness where rogue planets drift unseen. It's a friendly darkness, familiar and warm. The darkness of night in a place where you're known. Outside, the world continues its business. Traffic sounds, distant voices, the hum of infrastructure. Inside, you're protected, wrapped in blankets and calm. Let the images from tonight's journey soften and blur. The quasi-star, that enormous ember with a black hole at its core, can fade into a gentle reddish glow, warm rather than threatening, distant rather than immediate. The magnetars and blazars can quiet their violence, becoming mere concepts rather than visceral presences. The philosophical questions can settle into the back of your mind, available when you want them, but not demanding attention now. The universe is vast and strange, yes, but it's also patient. It has been here for 14 billion years. It can wait while you sleep. The quasi-stars burned out eons ago. They're not going anywhere. The supermassive black holes will continue their slow growth whether you're awake or asleep. Tomorrow or next week or next year, you can return to these wonders with fresh curiosity. For now, you've done enough. Think, if you like, of the light that has travelled so far to reach us. Photons that left distant stars thousands of years ago are just now arriving at Earth, bringing information about events that happened before any living human was born. That light passes through the darkness of space, crosses the emptiness between stars, survives the expansion of the universe itself, just to reach your small planet. Some of it enters your eyes when you look up at night. Some of it tells us about quasi-stars and the early universe. All of it connects us to something much larger than ourselves. But even that light can wait. Even the cosmic messengers can queue patiently while you rest. The universe is not demanding your attention right now. The stars will not mind if you close your eyes. Your body is heavy now, sinking into the surface beneath you. Your thoughts are slowing, becoming more diffuse, less structured. This is good. This is the natural progression towards sleep, the gradual dimming of conscious awareness. Let it happen. Don't fight it. The cosmic monsters will keep their secrets until you're ready to seek them again. Remember that you're part of this universe, made of the same atoms that make up stars and planets, subject to the same forces that shape galaxies. The iron in your blood was forged in ancient supernovae. The oxygen you breathe was created by stellar nucleosynthesis. You're not separate from the cosmos. You're a temporary arrangement of cosmic material, briefly conscious, briefly wandering, briefly here. That's a beautiful thing, not a sad one. It means you belong. It means you're connected. It means that when you look up at the stars, you're seeing distant cousins, Other collections of atoms organised by the same forces that organised you. The universe is not alien. It's home in the deepest possible sense. And now, home is calling you to rest. Let your eyelids grow heavy. Let your thoughts grow quiet. Let the darkness be soft and welcoming, a blanket rather than a void. The journey is complete for tonight. The cosmic monsters have been explored, their strangeness contemplated, their lessons absorbed. What remains is the simple act of sleeping, the ancient rhythm of consciousness fading and returning, the trust that morning will come and you will wake. Breathe in, slowly. Breathe out, slowly. The stars are still there, twinkling silently, keeping their eternal vigil. The quasi-stars are gone, but their descendants, the supermassive black holes at the hearts of galaxies, spin on, patient and vast. The universe continues its expansion, carrying everything further from everything else, creating the empty space that keeps us safe from cosmic violence. And you, small and precious and briefly conscious, you can sleep now. The night is yours. The dreams, if they come, can be whatever you need them to be. Tomorrow will bring its own wonders, its own questions, its own chances to marvel at the strangeness of existence. But that's tomorrow. Right now there's only this, the darkness, the breath, the gradual fading. Let everything slow now. Let the final images dissolve like morning mist lifting from a quiet pond. The quasi-stars have drifted back to the beginning of time, where they belong. The magnetars have dimmed their impossible fields. The blazars have turned their beams elsewhere, leaving only the gentle darkness of ordinary night. Your breathing is soft now, almost imperceptible. Each inhale is a whisper, each exhale a sigh. The rhythm carries you, a gentle current flowing towards sleep. You don't have to steer, you don't have to navigate, the current knows where to go. The universe, for all its vastness, can fit inside a moment like this. All the stars and galaxies, all the black holes and neutron stars, all the theoretical monsters and observed wonders, they collapse into a single point of peaceful awareness, here, now, in the stillness before sleep. Your body is warm and heavy, sinking into softness. Your thoughts are scattered petals drifting on a still pond. There's nothing to do, nowhere to go, no problems to solve until morning. This is the gift of night. Permission to stop, to rest, to simply be. The cosmic monsters are far away and long ago. The questions will wait. The wonders will remain, patient and eternal, ready for whenever you choose to return to them. But not now. Now is for darkness and warmth and the slow unwinding of consciousness. One more breath, one more gentle release. The stars wheel overhead in their ancient patterns, indifferent and beautiful. And you, small sleeper, precious brief consciousness, you can finally let go. The night holds you, the universe turns, sleep well,